I wanted to show you, just give you a glimpse really at another way of processing your digital signals. When we did the RC filter, we wrote out a filter for our digital signal in the time domain. When we've just done the rolling average, the hand filter, the Hamming filter, it's a signal that operates in the time domain. So the calculation is all in the time domain. But you're probably lightly thinking, well, maybe if I want to filter my signal from some noise, maybe I should work in the frequency domain. Maybe the first thing I should do is actually convert my signal from the time domain to the frequency domain, and then apply a frequency in a filter in the frequency domain. You know, so to cut out all frequencies above a certain cutoff, or cut out all frequencies below a certain cutoff, and that in that way, it'll be much clearer how I'm operating in terms of frequency, how I'm cutting in terms of frequency. So that is another possibility when you have digital signals that is not really a possibility in analog world. So I'm going to show you a couple of examples of this fairly quickly. So the basic idea I've tried to sketch out here. So instead of kind of directly going in the time domain from your input signal upstairs here on the left to your output signal downstairs here on the left. Instead, let's first Fourier transform the input signal into the frequency domain. So we're going to plot it versus hertz rather than versus period in seconds. Then we'll process it in that frequency domain. So I'll show you examples of processing, but you might imagine a simple one will be, I'm only going to keep frequencies below a certain cutoff frequency, or I'm only going to keep frequencies above a certain cutoff frequency. That would be, you know, in a sense, a very obvious way of making a low pass or a high pass filter. And then once I apply that that processing in the frequency domain, I can then take the processed signal in the frequency domain and then inverse Fourier transform it back to the time domain. And so that's this second leg down here. I'm going to process it in some way, and then I'm going to inverse Fourier transform it back to a time domain signal. And then I've got, you know, what effectively I had before. I got my input signal turning into an output signal, but I did all my work in the frequency domain. Okay, so I'm going to show you two examples of doing this. One is called a brick wall filter, and the other one is called like a carpet cleaning filter, and they operate in two different ways. You'll see how they operate. The brick wall filter can be useful for the following type of problem. Supposing you had two signals, a higher frequency and a lower frequency, and you wanted to pick out one of those two. You want to look at the lower frequency signal. You're only interested in that. Or you want to look at the higher frequency signal. You're only interested in that. Then you can use, I'll show you how you use the brick wall filter to separate those two, to pick the low frequency out of the mix of the low and the high frequencies, or vice versa. The second one, this carpet cleaning filter, that's where you have a problem. Supposing you have a signal of a certain frequency, but you have noise. You have white noise, random noise. And you want to pick out your signal from the white or random noise. So again, you can do that in the time domain, in the frequency domain, not with a cut at a certain frequency, but rather with a cut requiring a certain amplitude in the frequency domain. And so you'll see how that works. So this is basically how the brick wall filter works. this input upstairs here on the top left is just a superposition of two frequencies. So I think I made this one from one frequency and another frequency that's twice the first frequency. So just combine those two signals together. So let's imagine we're interested in the lower frequency. So I can transform that signal into the frequency domain. And that's what I did here. So this is the Fourier transform of this signal. Actually here, if you remember, the Fourier transform has positive frequencies and negative frequencies. Often in the past, we were keeping the positive ones and cutting off the negative ones. But there's positive and negative ones when you do the Fourier transform. And so I plotted them all here. Here's 0. Here's the highest positive frequency, highest negative frequency. And these two spikes here in blue, or these two spikes here in blue, are the two frequencies that I mixed in the original data. So supposing you wanted to just see, to filter out the low frequency, you could imagine you put a cut somewhere between the low frequency and the high frequency on the negative side, somewhere between the high frequency and the low frequency on the positive frequency side. And you only keep the frequencies with the lower magnitude, and you remove that part of the spectrum, the frequency spectrum that has the frequencies with a higher magnitude. And so you can just cut here on the left, cut here on the right, to remove the higher frequency here, remove the higher frequency here, and then Fourier transform back. And after the inverse Fourier transform, this is your output of your brick wall filter. So this is the low frequency in this data that was a combination of that low frequency and another higher frequency. And so this is where the name comes from. It's really just a brick wall in the frequency domain. You build this brick wall in the frequency domain, and if you blow it, if you want to be a low pass filter, you keep that stuff and you just zero all the stuff to the higher side of the brick wall, or vice versa. If you want to filter out the low frequencies, you throw the low frequencies away, keep the stuff to the higher side of the brick wall. So that's a very simple procedure. So it seems like, why would you ever not do that? And there are reasons you would not do that, because it's not quite as simple as that. If you notice here, do you see these kind of ripples on the amplitude? They're particularly large at the ends, at the bookends. So in the center, it looks kind of a constant amplitude, but on the far left and far right, there are ripples. And so this is an artifact of this filtering. That wherever you put that brick wall filter frequency, you get that frequency in your data, in the output of your data. If you had an infinitely long signal to the left and the right, you wouldn't have this problem. But if you have finite signal to the left and right, you pick up the cutoff frequency or the brick wall frequency in your data. It is superimposed with the signal and the amplitude of the signal. So that is a problem with that type of signal. It's called it's called the Gibbs phenomenon, and it's similar to, it's related to Fourier transforms. It's related to, for example, if you put a square, you can think of a rectangular pulse as being made up of many superposition of sine waves. Well, if you cut that off at not infinite high frequencies, but at some finite frequencies, on the edges of the rectangular pulse, you get these little wiggles, and that's Gibbs phenomena, and this is Gibbs phenomena. It's because you're either here we're truncating a kind of frequency space or a time domain, and likewise in that case of a square wave pulse with many sinusoidal signals, if you truncate it, you get this Gibbs phenomenon.
In case of case of the, let's say, this signal and then there's a white noise.
Mhm.
Will it work then?
Yeah, so let me show you the other one. The other example is for noise. So that's a very good question. Because this doesn't work that well for noise. If you think about it, white noise is typically spread everywhere. So, you know, this will cut out some of your white noise, but not all of your white noise. So this is not great for white noise. But carpet cleaning, so getting rid of noise is often called cleaning rather than filtering. So here's an example of the kind of carpet cleaning. So this signal here is exactly the circumstance you're describing. It's a superposition of a single sinusoidal signal with some random noise, with some white noise. And so again, if you take a Fourier transform of that, put it in the, it looks very messy here on the top left. If you take a Fourier transform of it into the frequency domain, you get this frequency spectrum here. So again, this is, I'm keeping negative and positive frequencies in this. So zeros in the center and high frequencies at the far right or the far left. These two spikes here, those two spikes are the signal. So that's the frequency of the signal. And then all the remaining hash here is the white noise. So, you know, you could try and put a little window, rather than just a brick wall, you could put two brick walls, right, around either side of the frequency of your signal. Or you could say, well, look, I'm only going to keep bins in my frequency domain that have a signal above a certain threshold, a certain minimum amplitude. So this is not this cut here is not a frequency cut. It's kind of an amplitude cut in the frequency domain. So if you're above this red line, I'm going to keep you. And if you're below this red line, I'm going to zero you. And so in this case, you see, I just keep this frequency here and this frequency here, which correspond to the same frequency, the positive and negative. And then if I Fourier transform that back, you get this signal here. So it's very, very effectively picked out from, rather than a lot of noise superimposed on your signal, a very clean signal. So, you know, that almost looks like, well, why wouldn't you do that all the time? It looks so perfect. There's always a problem. So one problem you have is that, this may or may not be a problem for you, but when you convert into frequency domain, you know, you've got certain bins of frequency. And so when you convert into the frequency domain and you keep certain bins and then convert back, you may actually convert back to a different frequency than you started. Your signal frequency may have changed between binning and then converting it into the frequency domain and converting it back. So that is typically one problem with it, that you might change the precise frequency and actually the phase of your signal. Or maybe that's not, it doesn't matter to you, but it's not like a completely free lunch. You have distorted things.
What happens in LIGO?
Yeah, so LIGO uses, I mean, to be honest with you, I don't know all the details of LIGO at all. But certainly LIGO uses filtering in frequency domain. And I'm sure these are the kind of the building blocks of what they put together. I'm sure it's more sophisticated. So just to show you that those slides are not made up, that it really does work like this. This is and I put this in the class notes in Canvas. So this is the brick wall filter. If you remember, this is the one where we said if we got two different frequencies, so here I've got two different frequencies, omega 1, omega 2, that are a factor of 2 different. I'm going to generate, I'm just going to show you this quickly, generate some data that is a superposition of the X1 is the first lower frequency, X2 is the higher frequency. This is the superposition of the two frequencies. Here I didn't put any noise in. So this is how I made this signal here. This is that plot that I showed in the slide of the two frequencies. This is how this looks in the frequency domain. This is the Fourier transform. But I wanted to show you this too. This is what's called the power spectrum density. So the Fourier transform, the value of any particular bin in the Fourier transform is a complex quantity. So it has an amplitude, which is the size of that frequency in the data, has a phase, which is, you know, how much cosine or sine is in the data. So the frequency of that, the phase of that signal. The power density, power spectrum density is basically like a square of the Fourier transform. So it's the value of the Fourier transform, which is a complex number, times its complex conjugate. So that gives you a real number. And so this second plot here is actually the power density rather than the Fourier transform. That brick wall filter is normally more effective if you apply it to the power spectrum distribution rather than the frequency distribution. So I'm sure they did that in LIDA. Because that gets around the problem of having you know, complex numbers in your Fourier transform. It also shows you that that spectrum is literally how much power is radiated at each frequency. So it's a very sort of clean thing to look at to try and separate the frequencies. So I did my filtering in the last example by applying the brick wall actually on this guy here. And as I say, I just cut to eliminate the high frequencies, keep the low frequencies. And when I apply that cut, here's the frequency that came out. Here's the Fourier transform that I made that frequency from. Here's the power distribution. It just has the lower frequencies in it and not the higher ones. And then just to show you again, this is the carpet cleaning filter that I put in the class notes. So in this one, it's the same code, but I just changed it a tiny bit. I'm just going to have one signal. So the amplitude of the first one is 1. The amplitude of the second one is 0. So I've just got one sinusoidal signal, but now I've switched on the noise. And the noise, if we go down here where I build the signal, is the sum of the two sinusoidal signals, but one of them 0. It's a bit silly. And plus the noise. So here I'm adding to the non-zero signal this random noise created in this way with this random function. So again, then I just plot it. I plot it in the time domain. I plot it in the frequency domain. We saw this one before. This is what it looks like in the in this power spectrum density, the square of the complex amplitude in the frequency domain. And again, here you see, because this is a square, right, the signal becomes much clearer with respect to the noise. And then I can just put a cut here. So I put a cut at 50. The amplitude have to be bigger than 50 and to clean up the spectrum. And when I apply that cut, this was the final output, just the single frequency. I didn't see any noise there. Here is the frequency spectrum, and here's the power density spectrum. And so they're very simple and straightforward to apply those two ways of picking one frequency from another frequency, or picking a frequency from noise.